Hello Flight Sim developers, welcome to part 3 of this series. I'm afraid it took a little bit longer than I anticipated, but that was mostly because I was having fun in C++, and there were some things, shortcomings, bugs that I found in SimConnect that I needed to investigate and report. But here we are. In the previous lesson, we just looked basically at connecting to SimConnect and then the simulator and exchanging some messages, including handling exception messages. In this lesson, we're going to look at obtaining data from the simulator and then parsing the results. Okay, so we're talking about transferring data from the simulator into our program. You can ask the simulator about many aspects of what is happening, both within the world, but also within the aircraft that the user is using and the other aircrafts or vehicles that can be shown within the simulator. Also, you can ask about the flight plan. There is a huge list of simulation variables available, and you can find them in the SDK documentation. Originally, this list was a lot shorter because there were fewer aircraft available, but also because the simulator was mainly concerned with just simulating the world, and simulating correctly what is happening inside the aircraft was often left outside of it. This means, of course, that add-on aircraft could then add their own simulations of the systems within those aircraft, and they wanted to add local variables to contain that state. This means that you get a lot larger list of variables. Microsoft Flight Simulator 2020 has a lot more default aircraft with more complex internals, and several of these are not built by Asobo or Microsoft themselves, but by external suppliers. So the list has grown. Now, when we request the data from the simulator, we do that in blocks. The reason for that is, well, let's just suppose we have 3 values, A, B, and C. Over time, those values will change, but they might not change at the same time. So suppose that sometime after we initially get these values, only A changes, and then sometime later, A changes again together with B. And a little bit after that, A together with C, but not B. And then finally, we could get another B without A or C changing. And you see the problem. If we request each value by value, then there is a lot of to and fro between our application and what is happening in the simulator. And that is wasting time and effort. So instead, what happens is we put those values together in a block. This block, for example, could contain A, B, and C. And now when we request this data, we get all of them at the same time. If we then want to know if anything changed and request it again, we will get the same block again and find out that just A changed. But we still get B and C. And of course, after time, in this case, we would then get A and B changed, but C still the same. This is very efficient. It might not always be what we want, but we'll get on that later. So what we first need to do is define how that block is built up. We call this a data definition. Every item must be added to the block in order. You can specify what you want and how you want it. The simulator can convert unit for us. So if it's a length or a height, then we get it in feet or in meters or even in centimeters or yards or nautical miles. We tell the simulator what we want. It will convert it for us before it sends over the block of data. Also, you can specify the value type within the block. For example, if we know that the value always is an integer, we can use an integer. If we know it has digits behind the period, then we can use a floating point or a double value. There is no Boolean value, but we can use an integer and it will get a 0 or 1, probably because there was no Boolean type in C when they made the SimConnect API. Strings, of course, are also available, and the most obvious forms of this are fixed length strings. For such a string, you first have to find out how long its maximum length can be, and then you choose the next up size and put that in the block. However, you can also decide that this is wasting too much space and use a variable size string. Now, the other way of getting that data is by using tagged data. In this case, we request tags to be added to every value within the block. Every item gets that, and it's sometimes referred to as a datum ID. You can request only to get change data while using those tags, and the simulator will then send us, well, let's call them incomplete blocks with only the data that has changed. So if we take our example of those A, B, and C values, we get a block that contains a tag followed by a value. So tag A, value A, tag B, value B, tag C, value C. Then if we have only a change in A, our next block will just have a tag A and a value A. This is not a problem for us because first, every value is prefixed with that tag, so we always know which value is the next one in the block, and we know how far we need to go because we have a maximum size of the block. So for the next A and B, we get a block with A and B, and A and C, we get a block with A and C, and so on and so on. This is, of course, a lot more efficient in the use of space, but it also means we no longer have a predictable layout of the block. Even stronger, if you had a non-tagged block, you could, with just fixed length strings, simply define a struct and then position that struct, so to speak, on top of the block and directly extract the values from there. But it's not that difficult to just write a few helper functions and then you can extract everything no matter which way you do this. So let's go to the actual call for the request. It's called SimConnect request data on SimObject because we're requesting data for a particular object within the simulator. There are 4 parameters that have default values, as you can see, and actually those default values are 0, and the simulator will interpret that as being not interesting for us. Let's start with the first. We have, of course, the SimConnect handle, and we have the request ID. Both of these we already looked at in the previous lesson. The next one is the define ID. This defines to our data definition, and just like request IDs and event IDs, it is up to us to actually choose a value for this. All the data within the block will refer to the same object within the simulator. So the next parameter is the ID of that object within the simulator. There are a number of predefined IDs that we can use. These are the, let's call them just ID for the user aircraft, for the user avatar, and for the current user. This sounds a bit like some overkill because you have the same kind of meaning several times. We'll get onto that. But the first thing, of course, if you don't use these predefined values, that means you have to scan for other IDs, and there are calls to do that. Note, SimObject ID user is, although still used in the documentation at several places, actually deprecated. So you're not supposed to use that anymore. Instead, you have to use the SimObject user aircraft or SimObject user avatar. Now, it is possible to use SimObject user current, and that will mean both of them. I haven't actually figured out yet what that does because it would be strange to ask, for example, the location when the avatar as well as the aircraft cannot be at the same location, but it might mean that you actually get 2 blocks of data. The next parameter is period, and this, of course, asks how often do we want the data. The simplest form of that is SimConnect period once. This means we tell the simulator, give me the data as it is now, and then just forget about this request. If we use SimConnect SimFrame, we ask the simulator to send the data every time it has finished the preparation of the rendering of a frame. This does not mean that the frame is visible on screen. It means that the simulator is ready to do that. This has to do with the difference potentially in speed of the simulator in the computer as it does its work versus the graphics card as it is actually rendering all those objects and things on your screen. It might be that there is so little to do that the simulator is finished a lot faster and can produce those frames faster than your graphics card can put them on screen. So this one is about how fast the simulator itself is. And then, of course, there's also the visual frame version of it. So this one means you get the data every time a new frame is put on screen. This is the value that is most often referred to when you talk about frames per second. And of course, there's also a very simple one which says every second. Now, the last one might sound strange, which is never, but this is of course the way to tell it to stop sending you the data. So you can start it for every second or every visual frame, and then at a certain moment, because your program is going to do other things, or you're not interested in the data anymore, you send this, and that will stop the data coming in on this particular request ID. The next thing are the flags. There are two flags. The first one is the flag that tells the simulator to only send us the data when it has changed. If we have an untagged block, that means we get all the data, including the ones that actually did change. If we have tagged, we only get the changed data within the block. Every data item is then prefixed with an ID, which is in fact a 32-bit integer. And if you use both, as I've already said, then you get only the changed items. If you want to specify both options, you have to use the bitwise OR to combine the flags. Then we have three remaining parameters, and those are for fine-tuning that period: origin, interval, and limit. Nothing will be sent until the amount specified by origin in periods has passed. So, for example, if we take period second, and then we specify for origin 5, then after we call the simulator, 5 seconds we get nothing before we get our first data block. Then interval is used how often, and it gives us a lot more variation possible. So we can say we don't want it every second, but we want it every 60 seconds if we want it just once a minute. And the last one, limit, is then of course the variation on the once, but then in varying amounts. So you can specify I want 10 times and after that stop. If any of these values is 0, then that particular parameter is ignored. So the next thing is then how to define our block. We build a data definition with the call SimConnect add to data definition. Again, we have here three parameters that have a default value as it is specified here, but let's go to the individual parameters. We'll start with SimConnect, which of course is our handle, and the define ID, which is the data definition block that we are building. The first call with a particular define ID actually creates that block as seen from SimConnect. The order of the calls determines the order of the items within the block. Items are packed in the block, but aligned at 4 bytes. This is actually only relevant if you use a variable length string. All the other values happen to be multiples of 4 bytes long. If you're using tagged data, then each one will be prefixed with a 32-bit integer, and that is the datum ID. So let's go to the name. Now, this is the simulation variable. Take a look in the SDK docs because there is a huge list, and be prepared. Most of them are dependent on the type of vehicle. So You can ask about data concerning, for example, a simple diesel engine, but if you don't have a propeller aircraft, then you won't get any data on that. Some examples of typical variables. Title is a very important one because that is the name, the full display name of the vehicle. A new one, which was introduced just a little bit back, is the livery name. You can actually request for an enumeration of all the liveries available for a particular type of aircraft, and the livery name then gives you the currently selected one. ATC ID is of course the ID that ATC uses for this aircraft, and engine type gives you a numeric value of the type of engine that this aircraft has. Then the unit's name, that is the unit you want to use. So this is what the simulator has to return the value in. For example, you can use any metric unit, millimeters, centimeters, meters, and kilometers for length. But you can also use inches, feet, yards, miles, and if it's a distance, you could use nautical miles. All of these actually, you have both abbreviations, if worthwhile, and full names. For strings and such, of course, you have to use null or an empty string because a unit is not a valid thing to choose there. Be careful here because the documentation mentions null between quotes, and I've made the mistake several times that I forgot about it and just simply copied quote null quote and then find out that I get an error because the unit null is unknown, and of course it just meant a null pointer. So then we have the datum type, and this is the type that the value has to be returned in the block. First one, of course, are the numeric types. We've got two integer types, 32-bit and a 64-bit. The 32 integer corresponds to an int or a long in Microsoft Visual Studio, and a long will correspond to the 64-bit integer. Then we have 32-bit and 64-bit floats, and those are respectively float and double. Then we have the strings, and they are available as fixed length 8, 32, 64, 128, 256, and for some particular reason 260 characters long. On the other hand, you can also use the variable string, and that will give you a string that is guaranteed to be zero terminated, because of course if you use an 8-byte long string fixed length and the text actually is 8 characters long, then you don't have any space left for the zero termination. But then, of course, because we need to align on 4 bytes boundaries, you need to make sure that you do that after you extracted or transmitted or put into the block a variable length string. There is a potential that this could be followed by 4 bytes of zeros. Currently, I've logged a message with Asobo, and they're checking to find out whether or not that is intentional or a bug, because actually, this is not documented. Not even the 4-byte alignment is documented. Then there are also a number of structs that you can use. Init position is used, as the name indicated, as the initial position. When you use a call to create an AI aircraft or some ground vehicle, you need, of course, to tell it where to put that vehicle. There you use init position, and there you can specify latitude, longitude, altitude, pitch bank heading, a boolean, whether or not it's on ground, and the airspeed. Then the next one is, of course, the marker state. Marker state is something that you will probably never see unless you are an add-on developer. It is made especially to allow add-on developers to find out the actual rendered boundaries of their models. Next one is waypoint, which is flight plan information. Then we have, of course, lat long alt, which is just like the first part of the init position. and XYZ, which is just generic for floats, and they are for other situations, for example, pitch bank heading, or you can use it as you like. The next value to look at is epsilon, and epsilon is specifically for numeric data. When you request data only when changed, this will specify how large a difference between the old value and the new value is considered significant. The default is 0, which means any change is significant. The last one then is the datum ID, and this is the numeric ID for that particular value in the tagged format. Okay, that was a lot of dry information, so now let's go to the editor and see what this looks like. Okay, so let's start with our test program. You see here, it's the same we used before. I already threw out all our previous commands. So let's start and put stuff in here. What we do here, of course, is define the data block and then perform the request. But first, let me show you a bit more of what is here on top. This is the handle messages method or function. It's the same as you've seen before. It can handle the exception messages, the open, the quit, and there is a new one here for SimObject data. There is already some stuff in there, but we'll go into that later. Above that, we have two functions for untagged and for tagged data. So we're going to go through both ways of receiving the data. There is a function hexdump that is used to show actually what is in the block of data. We've got the handle exception, which is just the same one as before. And here at top, we have a few helper functions. And here is what we're going to do. I've defined our request ID, and here is the define ID that we're going to use. They're just values 1, there's just one. And this is from the SDK, the names of the sim variables that we're going to request. I've also defined a struct, which matches with the initial version that we're going to use, which is going to use fixed length strings. And then this is for later when we're going to use tagged data, then these will be the tags. So let's go down and build the define block. Go here and let's start. And as I said, the first time you add something to the define block, that will create it. So add to data definition, give it the handle, and now our define ID. Next, the first field. So the first field is the title simvar, which is the descriptive name for this particular aircraft. And then it wants to know the units. Well, this is a string. So as I said, there are no units for the string. And then how do we want to get it? It is a value that can be max 128 characters. So we're going to use a SimConnect string 128. Like this. The other parameters all have default values. That's epsilon only if we ask for data only when changed, or the datum ID when we're going to use tagged. Not at the moment, so we'll leave it like this. Let's just copy this and reuse that for the 3 string fields. Later on, we also want the ATC ID and we want the ATC model. These are both strings that are maximum 10 characters long according to the SDK. So that means we can use a string 32. Like that. Then we had a boolean is user sim. Just as you spell it. And this one does need a units field because we want it returned as a boolean, even though there is no actual boolean type for transfer, so that will be just a normal 32-bit integer. Like that. Okay. Then the last 2 fields. And those are the current altitude. The first is named aircraft AGL for above ground level. And we want that reported in feet. Like this. And the last field is now not aircraft, but plane. And then simply altitude. Again, we want it in feet, and we want it transferred as a 32-bit integer. So this is all we need to do. We now have created and defined the data block, so we can request it. And we're going to use request data on SimObject. It wants to know the request ID. We made that, so. And then the definition ID. Now it wants to know on which object we want this. And we want it on the user's aircraft. And let's just ask it once. The remainder of the parameters all again have defaults, and we're not going to change anything for now. So let's do it like this. And see if we've done everything correct according to the compiler. Yes. Well then, let's see what it does. And here it is. I'll make that a little bit bigger. And you see here at the top, it connected to Microsoft Flight Simulator, and then we received a SimObject data for request 1, that's us. Object this, that is the digital value of that user aircraft value. For define ID 1, there are 6 items in here. This is the only in a group of 1, which is for a later part. And we have 216 bytes of data. And this is what the hex dump function does very nicely. It shows us the hex values in there. And if it is printable ASCII, then it gives the printable ASCII version here on the right. But of course, we haven't done anything to actually extract the data. So what it shows here beyond that is pure garbage. So let's see if we can change that. We go now up here to the handle messages, and we need to take a look at what is happening here when it receives a SimObject data message. Now, if you look here, I've put in already some typical checks. I'm just checking here, is this for our request? And if so, is it for our define ID? Of course, we haven't got any other define IDs in use, but it's just a good check. And then compute how many bytes of data we have in the block, print all the information. If the data is only sent when changed, that is also reflected in the flags in our message, so we can detect that. And the same is, of course, for whether or not we're using tagged data. Here's the call to hex dump. And then after that, we define data and then parse everything. And this is nice, but initially we're just going to map it on top. So we're going to make this a pointer. And we're going to cast the address of the location of that data. Like this. So now we have a pointer into that block of data, and we can just pretend that it's the struct. We're not going to use this for the moment, and we'll just change this from a dot to the arrow notation, and you see that immediately resolves any errors in here. And this should immediately give us already some data to print. Let's see what happens. Okay, this looks a lot better. Title, 404 Titan Air Ambulance. Yes, this is the user's aircraft. The ATC ID, PHDDG, interesting. And this is actually a bug in Flight Simulator. I have reported about this one. Here it should show a C404 as the text, but instead this is a reference to the field And because the field was not provided by the maker of this aircraft model, Flight Simulator was unable to retrieve it, and rather than returning an empty string, it returned the reference name. Yeah, too bad. This will be fixed later on. This aircraft is currently 99 feet above ground level, and that happens to be 171 feet below sea level. And yes, I put the aircraft in the Netherlands on an airfield that is below sea level. Too bad. But it's dry, don't worry. Okay, so this is a very simple way this works, but we're wasting a lot of message space to unused strings. So let's use those variable strings instead, and that means we need to reinstate the parse tagged and untagged, and then actually retrieve the data that way. Okay, we'll reverse these changes. Like this. And now we're going to the untagged method and fill it in. Okay, parse untagged. I'm going to use a bit more, how do you say, verbose programming here, just to show you how you could do this and set this up as a library. So there will be more here than you necessarily need to do, but it looks a lot cleaner, and it allows at the end to check whether or not we used all the data that was available. So let's start. First of all, we have a string, and I said we were going to use variable length strings. So instead of this, it's going to be type string v. Okay, like that. And the first thing we want to know is, okay, how long is that string? So let's define integer. We start with the title. And we have this buffer named PTR, pointer to bytes. And what we want to do is to character pointer. That's one of those useful functions at the top for PTR I. Like that. Then we now can safely copy that value into data. We have to use a secure string copy, otherwise the Visual Studio environment is going to complain about it. We're going to copy to data dot title from that same to character pointer. Like that. Now we want to move beyond this, and we need to take into account that the string might have a non-aligned number of characters. So first we're going to adjust the title length. To include the terminating 0 byte. And now if we're not aligned to a multiple of 4. We're going to add the remainder. Like that. And if we do it like this, as I said, it's a bit more than we need to do, but now it's pretty clear that we're back again. PTRI is the next character that we're going to do something with. So the second field is a Boolean. Now, the way integers, 32-bit integers, are stored, the least significant byte is the first one. So we can actually be very quick about that Boolean field. Is user sim is this. But of course, we do need to skip an entire 4 bytes. Sorry, T. Okay, next one, we'll copy this and take here ATC ID. And do the same for ATC model. Let's do it like this, that's a bit quicker. Okay, and then last we have 2 integers for the altitude above current level. And just once more for the above sea level. Okay. And this should work. We just need to make sure that we do some proper casts. It shouldn't hurt here, but he is correct. Okay. Like that. Run. Okay. So you see, actually we did get different values here. So probably there was something not entirely correct previously. And that is another bug in Microsoft Flight Simulator 2024. If the string, including its terminating 0 byte, precisely ends on a 4-byte boundary, you get an extra 4 bytes of zeros. So this will be fixed, but for the moment, this should have been 99 foot and the next one should have been above sea level. We can just do that here and say here, this plus 4, it's only for this one. Rebuild and run, and now you see again we have the correct values. By the way, if we're going to use tagged, this problem will disappear, but that's a different thing. Okay, so we've done mapping using a struct. We've done returning with variable length strings and then extracting it bit by bit. Let's do the tagged bit. So the difference with tagged is that we now need to go to our request and add those tags. We're not going to use epsilon, but just use this for datum ID and like that. Okay, let's do a bit of copy pasting to make it a bit faster. Number 2 is user. Number 3 is ATC ID. This one is ATC model. Altitude above ground level and altitude above sea level. Okay, and now we need to add the flag. So this one. Okay, check. Yes, we're now into the other one. So we need to again add a bit of parsing. Let's go up here. And here the approach will be different. We can now use a while because we're not certain if we're going to get all the fields. We have a count. We can just reuse that. Yes. So while we are still within the data block and we still haven't had all data items. And let's not forget to decrement that. Now we need to get the datum ID, like that. So now we know what kind of thing is coming. And we want to cast this to a datum ID so we can do a case and start with 0. If you find this, we just skip it. Ooh. And here we can now use actually the same code we had up there. Copy that here. And this way we now will do all the fields. Note that it doesn't really matter in which order we do it. We can just copy them all over. Here. That. And I think we missed one here. Is user. Let's copy that also from here. Okay. So we've each time incremented I. And that should be it. It's better to have them all with a block. Sorry about that. And do it nice. Yes. And you see, we again have our values, and you see that the data block is indeed a lot more compact. Okay, let's wrap this up. So basically, there are three ways we can get data. First way is that we can get the data in one unstructured blob and then map a struct on top of it. This is, of course, the simplest way to do things. You can immediately access the fields within your data as long as you make sure that all the definitions match what you told SimConnect on how you want that data to be received. But there are also a few cons. First of all, you need to copy the data out anyway because the memory that you are receiving for that message is owned by SimConnect. So if you keep pointers to it for a long time, those pointers will start pointing at other data, which is not something you want to do. The next thing is, of course, that you need to work with fixed length strings. If you want to use variable length strings, you cannot do that with a struct because you don't know how large that character array needs to be. And those strings have an additional problem. If the value actually maxes out the contents of that array of characters, then there won't be a terminating 0. So you have to be careful about copying the data out. And then the last thing is simply that you're wasting memory if you know in advance that only a few of the variables will actually change. So the second way to get the data is still to get it in an unstructured blob, but now extract the data field by field. Advantage is that you can now use those variable length strings, which can save you some memory. And you no longer have the risk of keeping pointers to memory you don't own, hopefully, because you need to copy it out, and that means you're getting the data into a safe location as soon as possible. But there are also a few cons here. It is more work. If you build a library for it, and you know me, I like to do that, then you only do that once. It is admittedly slightly slower if you are in the millisecond critical category. This is pretty rare, I dare say, unless you're actually writing an aircraft and modeling all the systems within that aircraft, then you might run into timing issues. But if you run into timing issues for this, then you're probably getting a lot of data that you need to process as fast as possible. So that is a pretty rare situation, but it's possible. And of course, because you're using an unstructured blob, you're getting all the variables that you have asked for. So if they don't change, then again, you're wasting a bit of memory. The third way is to get tagged data and extract the data one by one. Now, the advantage is that this is the safest way to do it because you always know exactly what item you're going to get, so what type it is and how you need to extract it. There's no risk of keeping memories, just like with the previous one. And there is a very efficient way you can now retrieve the data by using the only when changed flag as well. The disadvantage is, again, you need to write a bit of library work for that, and it is slightly slower if you're millisecond critical. Now, while we looked at the code, I ran into a few things that were unexpected compared to what the SDK documentation predicts. Unfortunately, you cannot avoid running from time to time into bugs, and those bugs might be either in the SimConnect library or in Microsoft Flight Simulator. Tough luck, there is no way to really prevent this. It's not that Asobo does this for fun, but they're also human, so there might be bugs. So, write tests for your code. This is very important, and I think it's a good thing to do always. Use those tests and rerun them often, even if your code does not change. Flight Simulator can change, and updates may introduce fresh issues because either the SDK changed or a call changed, and you need to adjust to that, or it might be new bugs that were introduced or reintroduced and unfortunately surfaced. So how about C++? Because this was mostly the C style of getting data. The library actually is quite a lot of stuff. It was quite a lot of fun writing it. That's me. There are lots of templates in there, and that is something we're going to do in the next lesson. I just think it's fun to do this. The hard work is in the library, and the whole goal is to make something that is as easy to use as possible. But as always, even if you stay on the C library, try to use as much of C++ as you can, because it will make for better and safer code. And set those warning levels as high as you can and treat them as errors, because it helps you fix bugs before they show up in production. So why was this part 3 so important? Well, most of what you do is dependent on data you receive from the simulator. So there are various other calls that also return data, and how they do that or how they return that data, the basics of processing that data will be the same. Sometimes you will get dedicated messages with fields, but sometimes you can get a blob. Add-ons can also add their own simvars, so there will be simvars that are not in the SDK documentation, but instead are in the documentation of the add-on you're trying to communicate with. These are called local variables. Another thing an add-on can do is actually use that blob method of transmitting data. These are called client data blocks, and they are mostly used when simvars are too limiting, or when there are so many items that they want to export or ask that it is simply too limiting to do that. And here the big example is the PMDG aircraft, because they simulate a lot of the systems in the aircraft, and they simulate as many as possible of all of the switches and lights and indicators within the cockpit. And that is so much that making simvars for all of that will simply be a lot of work, not just on the programming part, but also on keeping them up to date. So in that case, they simply defined a struct, which is in a header that they provide to you, and you can request that client data block and then map that struct on top of it. Okay, this is the end of part 3, and I admit I took way too long to prepare it, but apart from a lot of preparation work, let's just say real life intervened also, and there were some other things that needed attending to. Anyway, we'll continue The next lesson will be about the C++ version of doing this. So I will work on the library classes that I'm making to do this. If you've looked at the GitHub code, then you will have noticed that there is already some stuff in there. Take a look. Might be interesting to prepare for the next one. And as always, I'm doing this for the subs and likes. So if you like this, please leave one of those, and we'll see you in the next one.